Just one yes, cover first. Let me cover Phoenix yet. Yeah, that was today. I just did it. Oh, okay, we're just like the hours and thing. Yeah. Okay. You guys found that a lot or just I don't know that we really like I don't know. But, yeah. So you guys mixed it up. So that was two. Then we're after that. So.
Okay, time to.
I was like, no, I was like, who's my computer? I was there. Yeah, it was.
Okay. The room seems a little bit empty today. What's wrong?
It's Friday. I don't know if a lot of people wanted to come
You could use an app.
to. Yeah, it's true.
Was the 11 o'clock full?
It was not bad. It was pretty good actually. Right, 11 o'clock was fine.
I know a lot of people from this class want to go to the 11 o'clock class.
Well, what matters is that the best students are here in class, so we can start. Is there anybody online? One person only. Okay, well. So last time we started talking about refraction of light. And the idea there was that if you have two transparent materials, and this is the interface between them, incident light ray is always going to be split into a reflected light ray and a light ray that penetrates in the second medium that we call refracted light ray. So if the incident angle is theta 1 and the angle between the refracted light ray and the normal is angle theta 2, we said that if this first material has index of refraction n1 and the second material has index of refraction n2, we said that n1 multiplied by sine of the angle theta 1 is the same as n2 times sine of the angle theta 2. So this is Snell's law, and it is the base which describes how optical instruments, their objectives, their eyepieces work. Now, keep in mind that the index of refraction for any material is defined as the speed of light divided by the speed, the ratio of the speed of light in vacuum divided by the speed of light in the material itself. So the index of refraction for any material is a number larger or equal to 1. For many materials, the index of refraction for different wavelengths is different. So for many materials, usually the shorter wavelengths experience less refraction. And as a result of that, you can observe, and I couldn't put together well visible demonstration, but I'm going to draw it by hand. As a result of that, if you have, let's say, some material, transparent material like glass or some plastic, and if you shine white light on it, on the other side, you're going to see that this white light decomposed into the entire spectrum, visible spectrum of light. So what you're going to see usually here is going to be, keep in mind that you have two stage refraction here. On the first interface, you have refraction, and you have also refraction on the second interface on this side of the prism. And the result is going to be, let's say, the blue light is going to be this way, the blue. And after that, you have green and yellow, green, yellow, and red. So this phenomenon is called dispersion of light. So, and it especially in the past, it was widely used. It was widely used for in spectrometers. So usually what you do is, let's say you have a sample of some material and you want to figure out, let's say, its composition, elemental composition. And what you do is you take that sample of your material and you either burn it or pass a current through it or heat it up to high temperature until it starts emitting light. And this emitted light is after that analyzed with a prism like this. And we know that each element and also every compound has characteristic emission spectral lines. And the intensity of the spectral lines depends upon the concentration of the element that you're analyzing. So old spectrometers were based on prisms like this, while, well, nowadays, instead of prisms like this, we use alternative methods, as we're going to see in the following chapter. Okay, now, oh, by the way, we have to, so you probably already have the practice test for the next midterm. So start looking at it, and we're probably going to have the test not this coming week, but the week after that. Chapter 26 is, well, it is a relatively long chapter, so we probably will need the entire next week to go over that chapter. And the homework assignment has to be done. So this homework assignment also is not that short, but this is because the chapter is long. The chapter contains many elements, and many of those elements actually are useful for practical applications that concern you. So we just have to work all the examples from chapter 26, which is going to take us probably most of the next week. And after that, the week after that, we will do the last midterm, like always, of the last 3 chapters. Okay, so now looking at the diagram of refraction of light. So usually we said the reflected light ray, we just don't show, just because we don't study it right now. But can you tell me, looking at this diagram, which one is larger index of refraction, N1 or N2? Well, the rule is that when the light enters optically denser medium in which the speed of propagation is smaller compared with the speed of propagation of light in the first medium. In that case, the refracted light ray gets closer to the normal. So N2 is larger than N1. In other words, the speed of propagation of light in the second medium is smaller than the speed of propagation of light in the first medium. But of course, if you have the opposite situation, here is again the incoming light ray, and here is N1, N2 smaller than N1. In this case, the light is going to be refracted this way. So this is theta 1, this is theta 2. The light is going to be refracted this way. And you look, if you increase the incident angle, the angle of incidence from theta 1, make it a little bit larger, you're eventually going to have a refracted light ray this way, according to our the formula. And eventually, at some angle of incidence, the refracted light ray is going to skim over the surface, over the interface of the two materials. So any further increase of the angle of incidence you would expect the refracted light ray to go back. But this is impossible because the refracted light ray has to propagate in this optically faster medium. And if it doesn't enter it at all, it shouldn't be there. In other words, if you exceed certain angle of incidence, the refracted light ray disappears completely, which means that the reflected light ray, which is always present, is going to get all of the intensity of the incoming light. The light ray that enters the second material is not going to be present anymore. Yes.
Are questions from chapter 26 on the practice test as well?
Questions from chapter 26 are in the practice test. Yes. Yes.
Sorry. So what you're saying is if the light ray coming in is refracted so that it's exactly horizontal to the new medium, it will magnify the light that's going out incidentally?
Something like this. So let me try to clarify it. If you exceed this angle, the angle corresponds, the incident angle right here, if you exceed the value which provides angle of refraction 90 degrees, if you exceed it, the refracted light ray is going to disappear completely. And all of the incoming intensity is going to be left for reflected light ray, because nothing is going to enter and get refracted. So this is what we call total internal reflection. So suddenly, look, you suddenly, once you cross this angle, you suddenly see that the reflected light ray becomes more intense. This is what you see. In other words, everything that comes in bounces back. Nothing enters in the second medium. Yes.
And then since you're talking about, is it coming in more vertical or more horizontal? Like which way is exceeding the?
So this angle here is the critical angle. So this angle is the critical angle right here, the angle after which theta 2 becomes equal to 90 degrees. You have to keep asking until I figure out exactly what the issue is.
So like the angle that gives all the intensity in the light going up, like would it have to be more like coming in more vertical or coming in more horizontal to do that?
It has to come at a larger angle with respect to the normal, so it has to be more horizontal.
Okay.
Yeah, in this diagram.
Also to continue to clarify, so at that angle, there would no longer be any refraction, it would be total reflection, is that?
Well, the critical angle, the things, so you can never have exactly the right angle so that the refracted light ray to be skimming the surface. You know, it is, you have, if you had calculus, you know that the continuum is interesting thing. You can never hit exactly this, the exact number, right? So basically, you have some critical angle and you can calculate it. Experimentally, you probably can never get it. Let's calculate the critical angle. So you want n1 times sine of this critical angle to be equal to n2 times sine of 90 degrees. Right? This is what you want for the critical angle. But sine of 90 degrees is equal to 1, right? This is 1. And therefore, the critical angle has sine equal to n2 divided by n1. So look, in order this to make sense, sine of any number, sine of any angle is a number smaller than 1 or equal to 1. So in order to have this expression smaller or equal to 1, n2 has to be smaller or equal to n1, which is what we said, n2 is smaller than n1, in order to have this total internal reflection. And look, total internal reflection is what the fiber optic cables are based on. So the fiber optic cable has a core, some plastic material that is transparent, and it is surrounded by cladding, another transparent material with index of refraction n2 that is smaller than the index of refraction of the core. And therefore, a light ray that comes in the core at an angle exceeding the critical angle is going to not penetrate the cladding at all, but it is going to be completely reflected, totally reflected. Again and again and again until it emerges on the other side of the fiber optic cable, with practically no losses. So you may have a very long, kilometer-long fiber optic cable. Whatever you shine on this side is going to pretty much with no losses is going to show up on the other side. Especially if instead of a visible light, you prefer to infrared infrared because infrared is less absorbed by standard materials used for fiber optics. So look, the cladding in general is present to protect the core from scratching and mechanical damage. Instead of cladding, you may have just air. Air has index of refraction equal to 1, so it's going to do a good job. And here is something like a fiber optic cable surrounded by air. Just core is necessary. And if I turn on the lights, you're going to see that when I exceed the angle of incidence equal to the critical angle, you're going to see how, let's see. So of course, it has to be also clean surface because the presence of chalk is going to see the light. You see how the light is reflected. If, well, of course, I have to exceed like this. So this is how you do fiber optic cables in a simple way. Of course, there is some absorption in any material, so nothing is perfect. So periodically you have to take this light signal and amplify it because you lose some intensity. But no intensity is going to get, no light is going to get out of the fiber optic cable, and this is what you want. You want as much as possible to reach the other side.
What keeps it in there? What keeps that light?
Reflection. Total internal reflection. No refracted light ray. No light ray is able to, you see, is able to get out of this material. Just because I'm doing total internal reflection. And by the way, you use this total internal reflection in many other optical instruments where you want, instead of trying to get a perfect mirror, sometimes it is better, it is easier to have a plastic material that is acting as a mirror because of total internal reflection. Let me try to show it right here. Let's take maybe green, white, laser, or no, let's use this laser because here is this laser. Let's get only 3 light rays. Let me turn off a little bit the lights. Yes, you see it pretty well now. And let's do total internal reflection right here. Start maybe this way. Now you see refraction, right? You have refraction from this surface, refraction for this surface eventually. Now let's try to exceed the critical angle until we lose the entire. Let's see if we can, right here. Here it is. Everything is reflected now from those 2 sides and comes back. Well, this is because I exceed the critical angle here at this surface. If I don't exceed the critical angle, here it is, you start having the refraction. Exceed that angle. Here it is, everything is coming back. Totally internal reflection from here and from here, everything is coming back. And in binoculars, in order to have stereo vision, you want the 2 objectives of the 2 sides to be separated as much as possible in order to have good stereo vision. And well, the light comes in, it is, instead of mirrors, it is reflected from a prism shaped like material like this, and eventually gets into the eyepiece after this reflection. Here. Okay, now knowing this about total internal reflection, let's look at maybe something like this. Yeah. Okay. So basically, what I'm showing here is that if you have a shape like this, and you have incoming light, monochromatic to avoid the dispersion, monochromatic light, this red light, it is eventually after refraction here and here, it is going to come this way, as you see. But it is coming this way, but eventually you see that the three light rays eventually are going to intersect somewhere here. And maybe make it a little bit. Oops, lost the. Oh, lost the source. Let's see again. You see that the light rays that are going on this side are not exactly parallel. They eventually intersect, maybe far away, but I'm exaggerating here. They are going to intersect somewhere. Maybe somewhere here. Now, if I place a second prism like this to make it more symmetric, I'm going to eventually have a point in which, or at least an area in which the light rays that come in parallel here in horizontal directions are going to intersect at some area right here. If I shape this material appropriately, probably something close to spherical surface on this side, spherical surface close to a spherical surface on the other side, I am going to be able to create a single focal point. All light rays that come in horizontally are going to enter and hit this single focal point. And this is what a converging lens does. So a converging lens is shaped in such a way that any light ray that comes in parallel to the principal axis is going to go through the focal point, a unique point on the other end, on the other side of the lens. It's going to go here. Here is the focal point. Another light ray may be coming this way, again, parallel to the principal axis, is also going to go exactly through the same focal point. So we call this lens converging lens. We're going to work with thin lenses, which means that the thickness of the lens itself can be completely neglected, taken to be much smaller than the other distances in our optical system. Now, look, in general, many converging lenses are symmetric, which invites you to have two focal points on the two sides of the lens because of the symmetry of the system. So you have focal point on this side, you have another focal point on this side. In order to, yes,
Are those equidistant from the?
yes, yes, they are. So of course, the distance between the lens and the focal point is what we call focal length of the lens. In order to form an image, you need at least two easy to trace light rays. The first easy to trace light ray is a ray that comes in parallel to the principal axis, as shown here on the diagram. The second easy to trace light ray would be a light ray that comes to the focal point, let's say to the focal point on the left-hand side. So a light ray that comes in through the focal point is going to be refracted, and on the other side, it is going to emerge parallel to the principal axis. And the third easy to trace light ray would be a light ray that comes in through the center of the lens. That light ray is going to emerge with no change of its direction. So usually 2 light rays are sufficient to form an image, but we have 3 easy to trace light rays, and we can always form an image using those. Now, let's see how to form an image. Let's do image formation from a converging lens. And depending upon where the object is located with respect to the focal point, the properties of the image are going to be different. So let's consider the case of a converging lens used as a magnifying glass. So here is a converging lens, principal axis like always, and let's say focal point here and symmetry on the other side here. So actually, if this is twice the focal length, in order to form, well, you don't need that point at this for this construction, but in order to use this converging lens as a magnifying glass, you have to place your object between the focal point and the lens itself. So let's have the object there, and now let's form the image. Look, one easy to trace light ray would be parallel to the principal axis. On the other side, it is going to go through the focal point. Yes. And another light ray that you can trace easily. Of course, you can pass a light ray this way to the center, but instead, I'm going to pass a light ray like this, so that its continuation goes to the focal point on the left. That light ray is going to emerge parallel to the principal axis on the other side. So you see that the two refracted light rays never intersect. But an observer that catches those two light rays, here is the eye of that observer is going to detect this light ray and going to say, well, the image is going to be somewhere here. And his brain also is going to detect the second light ray, and he's going to say, well, the image is going to be somewhere here. And therefore, the image is going to be formed, let's say, let me make it more visible. The image is going to be formed here. It happens in such a way that the light rays are not very straight, but you have, on paper, you can do a better job. Now, since the image is formed from continuation of light rays rather than from real light rays, and it is also on this side, on the left-hand side of the lens, rather than normally on the right-hand side of the lens, the image is virtual. It is magnified, right? You see that it is larger size than, and it is upright rather than inverted. So those are the properties of this image when you place the object between the focal point and the lens itself. Now, of course, we deduced the properties of the image from our construction. But those properties could have been calculated using an equation similar to the mirror equation. So exactly the way we prove the mirror equation using triangles, similar triangles, we can, exactly the same way, we can prove a similar equation for lenses, thin lenses. So let's define the distances right here. The distance between the object and the lens, of course, is DO. The distance between the image and the lens is distance DI. The focal point and the lens are separated by a distance called, of course, focal length of the lens. This is the focal length of the lens. And of course, you have the height of the object is HO, the height of the image is HI. And the following equation is derived using similar triangles, exactly the way we did with mirrors. So you have that 1 over DO plus 1 over DI is equal to 1 over F. Well, instead of calling this mirror equation, now we call it thin lens equation. And in a similar manner, linear magnification, M, defined as HI over HO, can be proven to be exactly equal to DI divided by DO with negative algebraic sign. However, those two simple equations, they give you all the information that is needed to deduce the properties of the images. However, they only work if you follow appropriate sign convention. And the sign convention for lenses is, in a sense, exactly opposite to the sign convention for mirrors. So let's write down the sign convention for lenses. The focal length is a positive number if the lens is a converging lens, like the lens that we worked until now. And the focal length is a negative number if the lens is diverging lens that we're going to deal with in a minute. Well, for us, DO is always going to be positive because we're always going to place our object on the left-hand side, to the left of the lens. DO is always positive for us. But for complicated, more complicated optical instruments that contain maybe multiple lenses and mirrors, DO, so the image from one lens, let's say, can be used as an object for another lens. In that case, it may happen that DO is negative because the object may appear to be to the right of the lens. We're never going to encounter this situation, so I'm not going to consider it. And finally, here is the difference between lenses and mirrors. DI is a positive number if the image appears to the right of the lens. And a negative number if the image appears to the left of the lens. In the case of magnifying glass that is drawn here, DI has to be a negative number. You have to insert a negative algebraic sign for DI, otherwise the thin lens equation and the magnification equation are not going to work. And again, HO is always positive for us because we always place the object upside, right? But HI is going to be positive if the object is upright, and HI is going to be a negative number if the object is inverted. So for us, for the magnifying glass, HO is a positive number. At least the situation that we considered with the magnifying glass. Okay, any remarks and questions, issues? Okay, so well, we have enough time, but let me construct an image for the case when the object is placed at a distance twice longer than the focal length of the converging lens. That case is, let's draw it, and we're going to see what are the properties of that. So here is the principal axis. Let's say here is the focal point, and here is twice the focal point, twice the focal distance. If you place an object right here, let's construct the image. And by the way, this is an example that I'm giving, because this is how you use converging lenses for objectives of optical instruments, cameras, telescopes, and everything else. Objectives are converging lenses used in this regime. And let's construct the image. Here you have the first light ray, easy to trace. The second easy to trace light ray, maybe directly through the focal point, is going to emerge parallel to the principal axis, like this. Here is the image of your object. Properties of that image: it is real because it is formed by intersection of real light rays, not their continuation. It is formed on the right-hand side. So it is real, it is reduced in size. Reduced in size, and it is inverted. So of course, if you want to use this as an objective of a scope, you need to have a second system or a second set of lenses to form an eyepiece to observe this image and magnify it if you want a magnification. In the cases of cameras, you don't want magnification because you want the image to be formed in a specific small piece of the camera that is photosensitive, and the image is going to be formed there, exactly in the CCD camera spot. Next week, we're also going to consider the human eye. And the entire optical system of the human eye with multiple refracting materials can be summarized as a single converging lens. You want the image created by this single converging lens to fall exactly on the retina. And the retina, of course, is on the back of your eye, and it is a small area. So you want to form images of large objects in a small area. Therefore, you want them reduced in size. Yes.
What would a negative focal length look like for a diverging lens?
Well, here is a diverging lens with a negative focal length. So you have one focal point here again, and another focal point here. So the first easy to trace light ray coming in parallel is going to diverge in such a way that its continuation goes to the focal point. The second easy to trace light ray. So this is one. The second easy to trace light ray would be, well, a light ray that comes in, let's say, let's do it this way. A light ray that comes in, well, it is still divergent. Let me put a light ray that is going to come in like this. A light ray that is coming this way, so that its continuation is going to come to the second point, focal point, actually is going to emerge parallel to the principal axis. So this should be your second, and of course the third, and you can get a fourth easy to trace light ray, but in general we don't need it, so I'm not going to prove it. But here it is, a light ray that goes to the center is going to emerge, like always, with no change of its direction. So those are the three easy to trace light rays for diverging lens. And this distance is the focal length, and you measure that distance and you insert a negative algebraic sign for that distance. Now, I was still talking about converging lenses and the human eye. Notice that the converging lens of our eye is creating image that is inverted. So we're seeing the world upside down as strange as it seems, our brain is doing the processing and making the world upside rather than inverted. So we're going to continue with diverging lenses and with the human eye, and maybe some optical instruments here and there, microscope, telescope, next time. So please start looking at the homework assignment. It is relatively long homework assignment. And also start looking at the practice test problems. I actually took some homework assignment problems from chapter 26 and I put them in the practice test because I think that they're important for people that are biomedical majors. Okay, so have a nice weekend.